Good morning, y'all. So today we are going to be talking about limits day 2, continuity, and IVT. IVT stands for the intermediate value theorem, but we'll get that in a little bit. But first, we're going to talk about continuity. So we have two different functions. So the function here on the left is a continuous function. So notice how it's smooth and continuous, no breaks, no holes, nothing funny, anything going on. Function over on the right, g of x, is a discontinuous function. So it's probably piecewise. We got lots of different little pieces of functions going. We got a jump discontinuity. We have a removable discontinuity. We have another jump discontinuity, and we have a removable discontinuity. So we got holes, we got breaks, we got asymptotes, all different things that can cause a continuous function to be discontinuous. So when I want to talk about continuity at a point, what does that mean by continuity at a point? Continuity at a point means to prove a function is continuous through that point. So let's say I wanted to prove continuity right here. Well, looking at it graphically, y'all would probably tell me the same thing we decided earlier, that f of x is continuous. So yeah, it should be continuous at x equals 0. Okay, we can see it graphically. Graphs are easy, but remember, we talked about this a little last class with our graphical limits. Graphs are not perfect. They are an approximation. What is not necessarily perfect, but what is more truthful, it's going to actually prove things, is that algebra, is that actual proof that when I plug in numbers, I can prove that something is continuous. Okay, so if I want to show that a function is continuous at a point, there's three things I have to show. So let's say that point is x equals c. Then the first thing that I need to show is that f of c exists. So it doesn't matter what it equals. I just need to show that when I plug a value c into the function, I get a number out, which means that that point exists. Okay. The second thing that I need to show is that the limit as x approaches c of f of x is, sorry, I always mix these up. So going back a bit, f of c is defined and limit as x approaches c of f of x exists. Okay, they kind of mean the same thing, but we do use the different language for a reason. So f of c is defined is our first step. The limit as x of c, x approaches c of f of x exists. So our point is defined, our limit exists, and then the third is that we have to show that whatever value f of c is defined for is equal to the same value we find for our limit. Okay, so if the point is defined, the limit exists, and the point and the limit are the exact same number, then that would make a function continuous at that point. Okay, so let's look at an example. So I want to show that f of x is equal to x squared plus 3 is continuous at x equals 1. So first off, I need to show that f of 1 exists. So what can I do to show that f of 1 exists? Well, I can plug the number in and get a number out. So 1 squared plus 3 is equal to 1 plus 3, which equals 4. So first step, point exists. Second step, I want to show that the limit exists. Okay. Now, to show that the limit exists, remember there's two parts to a limit, the left side and the right side limit. Now, looking at this function, just if we were to think, do we have anything funny going on at x squared plus 3? No. We can plug one in, we already did, and it should be fine. But just for kind of helping you all out sake, when we want to find the limit, if we have anything kind of funny or weird going on, any sort of piecewise function, any sort of hole, something like that, then we want to show the limit as x approaches 1 from the left side we want to find the limit as x approaches 1 from the right side. And if those are both the same, then that tells us that our overall function is equal, our overall limit is equal to whatever that value is. If those are not the same, then that would mean that our overall limit doesn't exist, which would mean it would fail step 2. So from the left side and from the right side, I can't actually get to 1. So even though I'm approaching 1, I can't actually plug in 1 to see what the limit from each side would be. So 1 squared plus 3 is equal to 4. And 1 squared plus 3 is equal to 4. Those are equal to each other. So the limit as x approaches 1, the overall limit, would be equal to 4. So second step, limit as x approaches 1 exists. Okay. Now, yes, this might seem a little redundant, but that's kind of math. You kind of have to go through all the redundancies. You have to prove that, yes, it's true from every direction. So that it is 100% undeniably true that this function is continuous at x equals 1. So our third step, and this one is more of like, it kind of goes into your answer because this step is either true or not, and it basically gives you your answer. So step 3, f of 1 is equal to 4, which is equal to the limit as x approaches 1. So those are both equal to each other. So then we say therefore, which if you remember from your proofs in geometry, therefore we do those 3 dots in a triangle, which stands for therefore. So therefore, f of x is continuous at x equals 1. Just like that. Okay, now if any of these steps fail, so step 1 fails, step 2 fails, or step 3 fails, then you just go f of x is discontinuous. Also, if any of them fail, you get to stop immediately. You don't have to go through all 3 steps every time. If step 1 fails, you're done. Okay, just move on with the problem. But that is continuity. We're going to practice a little bit more in station 5 and station 6, so don't worry if you're like, Mr. Starbone, that was weird and new. Okay. Moving on down, we're going to talk about the intermediate value theorem. So to kind of help you out, what does intermediate mean? Well, intermediate means between. And the intermediate value theorem is essentially a theorem that tells us that the numbers between and a continuous function exist. It's pretty straightforward and simple. Okay. But the intermediate value theorem says that if f of x is continuous on the closed interval a to b, and what that means by closed interval is that means that I'm including a and b. So here at a and b, those points exist, okay? And n, so n being this y value right here, so n is a real number. Remember, a real number is just any number between negative infinity and positive infinity, any sort of decimal fraction, anything like that, a real number between f of a and f of b. Okay, so n is some y value that's in between the function's y value at x equals a and the function's y value at x equals b. Okay, so it has to be between them. Then there must exist an x value c in between a and b such that the function at c would be equal to n. Okay, now this kind of seems redundant, especially when you're looking at the picture. Like, well, yeah, Mr. Starbone, if that's my function and n's there, then yeah, there's going to be a c. But remember, graphs are just a helpful tool, but they're not proof. Graphs help us understand the situation going on. So we have to think about this almost without the graph. I covered up the graph in the camera, but obviously that doesn't happen for y'all watching this video. But We have to think about this without the graph and think about this algebraically. So I want to use IVT to prove that there's a root of f of x is equal to x cubed plus 3x minus 2 on 0 to 1. So on that interval. So what would it mean for there to be a root for this function? That would mean the function would have to equal 0 at some time in that interval, because anytime the y value is 0, the x value is a root. Okay. So we have our function f of x equals x cubed plus 3x minus 2, and I want to see if there's an f of c where my function would be equal to 0. Okay, so to do this, I'm going to use IVT. Okay, so for my function to have to equal 0, what f of a and f of b do I have to get? Well, I have to get one of them to be negative and one of them to be positive, because if I go from a negative number to a positive number, then I'm going to have to cross through 0 to get through that number. So let's just plug in our two endpoints. So f of 0 is equal to 0 cubed plus 3 times 0 minus 2, which is equal to negative 2. And f of 1 is equal to 1 cubed plus 3 times 1 minus 2, which is equal to positive 2. Okay. So looking at our math, we wanted to see if f of c could equal 0. So something in between 0 and 1, would that give us 0? We got negative 2 at f of 0 and positive 2 at f of 1. So we had to go from negative 2 to 2. Our function's continuous. It can't break. It can't do any weird jumping. We have to go from negative 2 to 2. So at some point, my function's going to have to cross through 0 to get from negative 2 to positive 2. So I already have all the math I need. So let's kind of put it into an answer. So f of 0 is less than 0, which is less than f of 1. So what I'm showing is that 0 is in between those two. Therefore, there exists an f of c equal to 0 on 0 to 1. Okay, so what I'm saying is because 0 is in between f of 0 and f of 1, there exists an f of c, so an x value in between a and b, where I could plug it in and get 0 on that interval 0 to 1. Okay, so kind of similar to our continuity is that we're going to kind of do our back work. We're going to show, okay, this has to be true, and then we're just going to put that into a final statement there at the end. Let's look at it from a table. So a little kind of different example, but the nice thing about this is I've already given you the numbers. Okay, so given values of the continuous function f of x are given in the table below. Prove that f of x must equal 3 sometime on the given interval. So our given interval is negative 1 to 10. So our closed interval is negative 1 to 10. Okay, so I need to show that at some point from an x value of negative 1 to an x value of 10, my function has to cross through 3. So I want to know what f of negative 1 is, which f of negative 1 is equal to negative 5. I can just pull it straight from the table. And I want to know what f of 10 is. F of 10 is 5, once again, pulling it straight from the table. And then is 3 in between negative 5 and 5? Yeah, so for my conclusion, I say f of negative 1 is less than 3, which is less than f of 10. So therefore, there exists an f of c equal to 0 on the closed interval 0 to 1. Okay, so the table's kind of nice. You don't even have to plug in numbers. That was the easiest, quickest math problem you've ever done. Just a lot of writing. Okay, last thing we're going to talk about, y'all, is finding limits algebraically. Okay, sometimes algebraic limits are super easy. Sometimes they require a little bit of extra work. Okay, but whenever you have an algebraic limit, so I have given you a limit as x approaches c, and I've given you a function. So you have an x value, you have a function to work with. Your first thing you should always try first is direct substitution. So always plug it in first. So the limit as x approaches 3 of 4x squared minus 1. 4 times 3 squared minus 1, that's equal to 4 times 9 minus 1, which equals 36 minus 1, which is equal to 35. So if I plug it in, I get a number out, that's my limit. Nice and easy. Okay, moving on along. Number 2. Okay, so I still have a function. I still have a number to plug in. Okay, so before I try to do any fancy work, I always want to plug it in, because when in doubt, I always want to plug in that number. Now, eventually, you might be able to start recognizing the situation where you're like, you know what, I think I know if I plug in this number, something weird's going to happen. But for now, we're just going to practice always plugging in a number. Okay, so -2 plus 2 over -2 squared minus 4, we get 0, and we would get 0. Okay, so that doesn't work. Okay, we can't have 0 divided by 0. That's a no-go. Okay, that's what we call indeterminate. We can't have an indeterminate answer. It literally says an answer we can't determine. So that doesn't make any sense. So now, let's see if we can maybe factor and reduce something. So we have x plus 2. My bottom can factor into x plus 2 and x minus 2. So let's get those x plus 2's to cancel out. So now we just have the limit as x approaches -2 of 1 over x minus 2. So now we can plug in again, -2 minus 2, and we get -1/4. Okay, so sometimes we're going to plug in. We're going to get an answer that doesn't work, whether it be indeterminate, whether it be divide by 0, which also isn't okay. We can't divide by 0, or something along those lines. So we have to factor. We have to see if we can simplify somehow to get down to an easier answer. Later on, like at the end of chapter 3, which is towards the end of this year, we're going to learn another way to do this type of question that's going to be super quick and easy. But we can't do that until we learn something else. So don't worry about it for right now. But for right now, plug in the number. If you get something that doesn't work, like a 0 over 0 or divide by 0, then factor, cancel if you can, that sort of deal. Okay. Number 3, when all else fails, think graphically. This will be especially helpful for one-side limits. So looking at this, we have the limit as x approaches 2 from the left side. Okay, so I am only concerned with the left side limit right now. I don't need to necessarily know both limits, what's happening from both sides. Okay, so also looking at it, I know if I plug in 2, I'm going to get 0 on the bottom, but let's do it just, to prove that we're like, yeah, I know this is going to happen, because math always helps you prove things. So 2 minus 2, which is equal to 1 to divide by 0, which is undefined, and that doesn't work. Okay, can't have an undefined limit. Doesn't really make sense. We can have a limit that doesn't exist, but we can't have a limit that equals undefined, because limits aren't defined or undefined. Doesn't make sense. All right. So now let's think about what's going on. Well, it's 1 over x minus 2. It's a rational function. If you were to guess what's happening there at 2, well, it's an asymptote. Okay. So to kind of help us out, I'm just going to draw a quick graph. 1, 2, 3, 4, 5. Okay, and this function would have a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 2 from that x minus 2 down here. Okay. And I'm going to cheat just a little bit because I know what this function looks like. Okay, but if you don't know what this function looks like, you can use a graph. I am also going to show you how to still do this algebraically. So don't worry if you're like, Mr. Arbone, I don't know how to graph rational functions. That's okay. You don't have to be able to graph these to do these. Okay, so now looking at our graph, if you were to look at this left-sided limit, where does it look like our function would go to? Well, it looks like it's going to go down to negative infinity, yeah? All the way down there, it's going to keep going on forever. Okay, well, a way that we can actually show this algebraically to prove it, so the limit as x approaches 2 from the left side, I have 1 over x minus 2. Okay, well, let's go ahead and plug in a number to the left of 2. So what's the first number just to the left of 2? Well, 1. So the limit as x approaches 2 from the left side is equal to 1 over 1 minus 2, which is equal to negative 1. Okay, I got a negative answer. Now, we know graphically what's happening. It's approaching an asymptote. So if I'm going negative as I approach an asymptote, as I get closer and closer, what do you think is going to happen? Well, we're probably going to get more negative. Well, let's just plug it in to try it out. So the limit as x approaches 2 from the left side, let's plug in 1.5, just a little bit closer. Well, that's going to give me 1 over negative 0.5, which would be equal to negative 2. If I did a little bit closer, the limit as x approaches 2 from the left side, let's plug in 1.9. So now I have 1 divided by negative 0.1, which is equal to negative 10. So as I get closer and closer, my number is getting more and more negative. Okay? If I got as close as possible, if I plugged in 1.99999 repeating on forever, am I going to get a super huge negative number? Yeah. So super huge negative number, another way to say that is just negative infinity. Okay, and we will talk about this a little bit more next time when we talk about infinite limits. Okay, but when you have a one-side limit as an asymptote, you can plug in a number from that side to know if it's going to be going to negative infinity or to positive infinity. All right, y'all. So we talked about 3 different things. We talked about continuity. We talked about intermediate value theorem, and we talked about algebraic limits. So you're going to be using all 3 in class today. Okay, so go ahead and practice through stations 5 through 8 and ask any questions if you need them.